Well, welcome back to this discussion about the attributes of functions and the analysis of function graphs. And in this video, we will be talking about looking at a graph and identifying domain and range, and also just a quick recollection about how do we identify the intercepts of a function or a relation just from the equation. So let's jump into that. Okay, so let's take a look at the domain and range of functions just by looking at their graph. So remember that the domain refers to the input values. If we're looking at a graph, our input values will be our x values. And so for the domain, we are going to be focusing on all possible values for x that are represented on the graph. Okay, so x-axis goes from left to right. So we are thinking about all possible x values that are represented on this graph. So we're going to be thinking how far to the left and how far to the right does this graph extend? Okay, and are there any breaks in it, or is it continuous? And for range, instead of going left to right, we're going to go least to greatest, or lowest to highest on our graph. So if I'm looking at this, and I'm looking at this first example, example A, and I'm trying to determine what is the domain, I want to think how far to the left and right does it go. Now I have added that little green bar to kind of show us how far to the left and how far to the right does this function go. And that green bar is there because we want to pull the x values from the x-axis. And so we can say that this domain is from -2 to +1. And then we want to think about, for this particular graph, will I include the endpoints? Because those endpoints are filled in, because they're solid, we can say that we will definitely include the endpoints, and we'll bracket the -2, and we will also bracket the 1. Now, if we're using an interval, we want to make sure that every x value between -2 and 1 is represented somewhere on the graph. In other words, there's no breaks. This is continuous. So from -2 to 1 looks good. So we can go ahead and say that that will be our domain. Now the range, that's going to be the least to the greatest y values. So here I have added a vertical bar showing how low to how high does this graph extend. And notice it goes down to 0 and up to 3. So our range is going to be from 0 to 3. And again, we double check and make sure that it's continuous from 0 to 3. There's no y values missing. And we will include the endpoints, so we will say that this is bracket 0 to 3 bracket. All right, for this next example, it's similar to the first one, except we have an open circle on the left and a closed circle here on the right. So if that's what I'm looking at, we're going to do the same thing. We're going to think how far to the left and how far to the right. And we have this -3 to +2 thing going on for left to right. And in this case, it's definitely continuous, but we will not include the -3 because of that open circle. So we will say our domain goes from -3 with a parenthesis this time, all the way over to 2. And for our range, oh, it's a tiny little thing, goes from 1 to 2, but it doesn't include the 1 because of that open circle. All right, so for the next one, we've added an arrow. Okay, so that makes it a little bit more interesting. So our domain, notice that we're going infinitely to the left, but we end right at 4 on the right. So think about all those x values on the x-axis, and how would you express that as an interval? And if you said -infinity to 4 with a bracket, you'd be absolutely right there. It goes infinitely to the left, so that's that -infinity piece. and it goes all the way to 4 and includes the 4 because of that closed-in circle on the right. Now notice it is continuous that entire way, so we can definitely use our interval notation there. Okay, our range. Our range is least to greatest, so we're going to go least, which is 0, up to, where does it end? What's the highest y value? Got to be careful here because that y value is increasing even off the graph. That arrow is showing us the behavior of the graph, so it's going infinitely up. So we're going to have a range of from 0 to positive infinity. The last one is the most interesting of all because we've got sections that are not actually connected. So we've got to be a little bit more careful. Our domain, we can start by thinking of left to right. So let's start by thinking how far to the left does this graph extend and then how far to the right. And we would say it definitely goes from 1 to 4. And then we want to make sure that every x value between 1 and 4 is represented if I want to use an interval. Okay, so let's look at this. If I go from 1 to 2, we're good up until we get to 2, but 2 is not included here. Oh, but it is here. So I've got everything from 1 to 2, and then from 2 to 3. Oh, we have a problem at 3. Oh, but we really don't because it picks up at this next line segment. Okay, so the only x value that is not represented between 1 and 4 is going to be 4. So we would say this is the interval from 1 to 4 and not include that 4. Now the range, this is a little bit different because look at those breaks in between. I can't use an interval here because it's not continuous between 1 and 3. Okay, so if I'm looking at this first line segment here, what is the y value? Well, that's a y value of 1. But then there's not another y value again until we hit 2. And then there's a break again until we hit 3. So really I have only 3 distinct y values and not everything in between them. So I'm going to list those y values in my list form, which is with those curly braces, 1, 2, 3. Okay, let's try another thing. This is where we are going to recall how to find an x-intercept and a y-intercept of a graph, okay? So when you have a function, you can definitely find the x-intercept by substituting a 0 in for y and solving for the x value. That makes sense, right? Because an x-intercept will have a coordinate of some x value comma 0, which means the 0 will always be y. Okay, and so the same is true for a y-intercept except the variables switch. For a y-intercept, we substitute a 0 in for x and we solve for y. Okay, so that's just a quickie reminder of that. And then we would want to make sure that we can read information from graphs. So let's consider this graph. And this graph we're going to say is the graph y is equal to g of x. A piecewise function, and it doesn't really have much going on except it's got different linear pieces that are all connected. Okay, so let's think about how do I identify from this graph what is g of -1? Well, in this case, -1 has replaced the x. So I'm looking for the y value where x is -1. So let's go to the graph and let's just trace over until I see, oh, here's where x is -1. What is the y value there? And we can definitely say that the y value there is 0. And so g of -1 is 0. We do the same thing for g of 3. We look for the x value of 3 on the graph. So remember, stay on the graph until you get to x equals 3. And now pick out the y value that corresponds. So the y value there is -4. How about g of G of -10? -10 isn't even on this graph. How can I answer this question? Well, what we can do is assume from this notation that this graph extends infinitely horizontally to the left. So g of negative 10 would be over here somewhere, but it will be on this horizontal line. And we can say that the y value there is 1. How about g of 10? Can you answer that one? Hopefully you are able to, because we can do the same thing on the right-hand side. We can assume that this behavior is constant all the way over to x equals 10. And we can say that g of 10 is negative 4. Now, is g of x a function? This goes back to what we talked about in our last video, and we need to apply the vertical line test. And in this case, there is not a single place I can draw a vertical line that will pass through that blue function more than once. So yes, this is a function. What is x when g of x is 1/2? Now this is kind of going backwards from what we did up here. We're saying g of x, which we know is y. We know that y is 1/2. What is the x? So let's go on our function until we hit a y value of 1/2. That's like halfway between 0 and 1, right? That's where I am. All right, so our x value there will be negative 3. Okay, how about this one? What is x when g of x is negative 2? Okay, so again, g of x is y. What is x when y is negative 2? So trace that graph until you hit a y value of negative 2. Now what's the x value? Right there. That should be 0. Now what's the domain of g of x? How far to the left and how far to the right does this graph go? Hopefully you were able to say that this is negative infinity to positive infinity because this graph goes infinitely to the left and infinitely to the right. Now how about the range? How low does this graph go? How far down does this go? And hopefully you are able to say that this is negative 4 and all the way up to positive 1. Now the tricky part here is, do I include the end points of my interval? And all you have to do there is decide, is there anywhere along here that there actually is a y value on the graph that is negative 4? And since all of these points have a y value of negative 4, we would definitely include negative 4, and likewise with positive 1. So we would bracket those. How about the x-intercept of g of x? That's where this blue graph crosses or touches the x-axis. And so we can see that that is happening at negative 1. And the y-intercept, that's the same thing with the y-axis. And we can see that this blue graph intersects the y-axis. It goes right through it at y equals negative 2. All right, that's it for this video. And in the next video, I want to talk about how to identify intervals where our function increases or decreases. And we're going to talk about maxes and mins there too. So I will see you then.